IFC is an open standard that has been developed by the software industry under the name Building Smart for the purpose of exchanging BIM models. It's supported by all BIM modeling programs. Using Open BIM Standard as a basis of collaboration means that designers, engineers, and contractors can collaborate safely and effectively with other disciplines using other software. Here you can see a collection of design, analytical, structural, mechanical, plumbing and electrical, fabrication, as well as construction and project management applications that all support IFC and Open BIM. Another important part of collaboration is how we share models. Today, that exchange typically mirrors the traditional 2D paper process. However, emerging BIM server technology is promising to make this file exchange process much easier. With a BIM server, teams will manage and control project information from a central BIM server database hosted either in-house or in the clouds. With new BIM server technology, models from the stakeholders will be uploaded to a central database where team members then can download the information they need for their jobs. And as changes happen, the team members will simply upload their changes back to the database. When a change is received, the BIM server will update the reference BIM model and then send a notice to the rest of the team letting them know that new information is available and ready for download. It will also track revisions and store them in the database. And with a BIM server, you could do more than just easily exchange models. You could also query the model for information and do things like view and track project materials, generate workflow approvals or schedules, bill of materials, estimates, and other reports. And this emerging technology is based on open standards, allowing team members using different softwares to easily plug in and participate in this new exchange process. Perhaps even more important to improving collaboration are new project delivery methods like IPD or Integrated Project Delivery, Design Assist, and others. Organizations like the Building Smart Alliance through their National BIM Standards initiatives, the AIA with their E202 documents, the AGC with their 300 series consensus docs, and others are driving Open BIM and helping to define model exchanges through their BIM execution planning documents. These new methods, planning documents and agreements, will help firms better collaborate and make it easy to share data by helping them define what information we exchange, BIM models, drawings, specifications, who owns the BIM model, and when, where, and how these exchanges will happen. Now, let's take a look more specifically at how this exchange works in a structural BIM process. For this presentation, we'll use the DC Riverside project as an example project that illustrates a BIM workflow between the architect and the structural engineer. As is typical today, teams in this project all use different BIM authoring tools, i.e. the tools they felt that worked best for their part of the design process. This project used the AIA documents E202-2008 and BIM Protocol Exhibit as a guide to manage the BIM model development and exchange. One of the benefits of this document is that it clearly defines who's responsible for what at the various stages of the model/project progression. This document introduces the concept of model LODs, or what we call level of development, for each stage in the design process. These LOD stages somewhat overlap the traditional workflows, but instead of 7 or 8 stages with very unique aspects, there's only 5, which focus on the development and the details of the BIM model and the responsibilities of each of the team members. While the stages appear linear from general to specific, it really promotes an iterative design process where team members are involved early and regularly review and exchange model information. For the purpose of this demonstration, we're going to focus on the LOD 200 and LOD 300 stages of model development. Now, this project started with an architect delivering 2 files, the LOD 200 model of the architect's early concept of the architecture and an LOD 200 model of the architect's early concept of the building structure. Being able to reference and reuse the architect's information is a huge benefit in working in a structural BIM workflow. Here you can see the 2 models together in the structural design software. Why 2 models? Well, having the architect's model as background geometry really helps me better understand the architect's intent and reduces the number of RFIs. Having the structural model means I don't have to start from scratch. Instead of having to import 2D CAD drawings and remodel the structure as I would in a traditional analysis program, I can reuse the structural geometry the architect has already created. In this model, floor slabs transferred in as 2D elements and beams and columns as 1D elements. From the architect's model, I can now begin to quickly verify and, when necessary, clean up the architect's information. This concept of being able to clean up an architect's model is another important requirement in structural BIM. As you know, architects and engineers think of structures differently. Architects tend to think in volumes. For example, in walls, they can sometimes mix up divisions of constructions. Essentially, they don't think of the structure as a real, coherent structural model needed for analysis. So, how do you go from the architect's model to a proper analytical model? Well, with traditional analysis software, this is either impossible, i.e. I have to remodel my building in my A&D software, or the cleanup is very tedious and time-consuming. Here's an example of what I'm talking about. Here we have a column as it would be designed in an architectural program. But we need different information. We need this schematic representation. You know, the plate, the foundation, the column, the beam, being described as bars and nodes. The ability to convert architectural objects into structural objects is another essential technology in structural BIM. And this conversion needs to happen in a semi-automatic way that allows for input from the engineer, keeping him in charge of how the analytical model goes together. In this view, you could see the two models together. I've grayed out the architectural model so you can clearly see the structural model that I'm working on. But again, having that architectural model in the background as reference geometry really helps me in my design process. So from the architect's early stage LOD 200 models, we would use rules of thumb and maybe some light analysis to return to the architect our early structural concept model, or the structural LOD 200 model. This model would be returned to the architect for validation before we continue. In this project, as is typical, the architect, owner, and contractor evaluated the early design and decided to make some changes based on cost, constructability, and aesthetics. Here you can see the architect's more refined LOD 300 model. In this project, the tower roof was simplified to a flat structure, and the east wing penthouse was developed into a full floor. From the architect's more developed LOD 300 model, we reworked our structural LOD 200 model to incorporate the changes. The result is a more developed LOD 300 structural model that is now ready for loading. Structural design programs should make it easy to create, apply, save, and edit loads and load combinations. Here you can see the live loads being applied to the floors in this project. Next, we set up the model for wind loads. In this example, we modeled the cladding as load panels. This gave us the ability to accurately represent the cladding mass and gather and distribute the wind loads, but not affect the stiffness of the structure, which, as you know, is important for seismic and other dynamic calculations. With the wind loads defined, we continued to add load and load combinations as necessary. Then, with the structure fully loaded, we moved on to analysis and design. Here, we're looking at the fundamental mode in the x-axis. And here, we're looking at an animation that represents the tower's central core deflecting under seismic excitation. Now, the central tower portion of this project required some special attention. The tower housed the building's mechanical systems and service cores, as well as a 6-story open atrium. Here you can see the y-axis bending moments on the tower atrium steel frame. And we can see these results graphically on the physical model of the structure. This ability to integrate the physical and the structural model means that we can visualize instantly how changes like editing a cross-section, adding some bracing, or moving a member will affect the physical structural model. This was important in this project as the tolerances for the mechanical systems were pretty tight. And of course, while we're working on the model, the program is automatically creating and updating our documentation. If we take a closer look at the service core, we can see the y-axis shear on the tower core walls. And because we can integrate design analysis with detailing, we could use these values to optimize the tower core's reinforcement. The same is true for foundations, shear walls, and other reinforced elements. And because all structures are tied to the ground, it's important to consider the effects design decisions have on the soil structure interface. Here you can see the bearing stresses in the soil, and if needed we could design piles for the supports. Having to switch between software packages or modules to accomplish foundation design presents another workflow bottleneck and opens up the possibilities for error. This is one of the reasons why we're starting to see general FEA software include geotechnical modeling that has traditionally only been available in specialized systems. Once we are finished with the design, we can begin to document our project. Here you can see a typical framing plan that was automatically generated from the 3D analytical model. Also, because we have maintained the architect's model in the background, we can give a much more complete representation of the structural system within its actual context. Here, the background geometry of the architect is displayed as grade in these drawings. And here are some section drawings generated from the model. Of course, these drawings are linked to the model, so they will automatically update as the design changes. And you could update these drawings and drive changes back to the model. Of course, these drawings can be exported out as DXF or DWG drawings or shared as PDFs. Having the 3D structural BIM model linked to the drawings gives engineers new ways to communicate their design ideas. Here we have a 3D PDF of the DC Riverside project. Using 3D PDF, we can create a building model that anyone can navigate and examine. Here we'll zoom in on the tower core. We can then change our rendering settings, and you can see the structure and the architecture together, giving engineers new ways to communicate their design ideas. Again, this presentation didn't require any special software or extra work. It comes as a side benefit of having the model and using open standards like 3D PDF. In this project, the architect's original design called for a tall, brace-free glass curtain wall in the lobby atrium. These large, unbraced column lengths required very large and expensive built-up cross-sections. After further review of the LOD 300 structural model, the architect decided the cost of these large columns was not worth the aesthetic effect. So, we conferred and jointly decided on the location of the new bracing. In this slide, the architect is notating in his architectural model one option for the location of the bracing. Here you can see the updated structural model in the structural design program. We reran the analysis, finalized the structural design, and then sent our changes back to the architect for his approval. During this process, we were able to track and store changes. In this case, the structural design program created a project archive of all of the iterations of our design. Using the same iterative workflows, this model was then further refined until the design was complete. And here you can see a final rendering of the architecture. Here you can see the models of the structure and the mechanical together. And lastly, here's all three together in the finished design. Well, that concludes today's webinar. I hope I was able to illustrate some of the benefits that working in a BIM workflow offers and leave you with some practical information that you can use when evaluating various structural design programs. Remember, BIM is not a technology, but a process, and having a structural design program that supports 3D object modeling, the foundation of building information modeling, BI modeling, or the integration of structural and analysis modeling, the integration of analysis, design, and detailing, and interoperability and collaboration with support for open standards that allow models to be shared with others, can make the transition to BIM much easier. In conclusion, I want to leave you with some links to additional resources you can use to explore and learn more about the topics that we discussed today. Don't worry about writing them down. I've archived them as well as a copy of today's presentation on www.sbimresources.com. That's www.sbimresources.com. In regards to earning credit for today's event, architects who registered with their AIA member number will automatically be submitted to the AIA for credit. Certificates for architects are available upon request. For engineers who registered with their member number, you will automatically be emailed a certificate of completion for your records. And please note my contact information. If you have any questions about receiving credits for today's presentation or on any of the topics that we discussed, feel free to email me.